Welcome to the Explainer. You know, the ground beneath our feet feels pretty solid, right? But in reality, it's in a constant slow-motion battle with itself. So today, we're going to dig into the science of geology. We're going to use its core principles to really understand the colossal forces that build mountains, that trigger volcanoes, and are, right now, shaping our world from the inside out.
So here's our game plan. First, we'll look at the restless engine that drives everything. Then we'll get into the actual building blocks of the planet itself. After that, we'll see the fire and fury that happens when those blocks meet. Then we'll zoom out to see how the surface gets sculpted over millions of years. And finally, we'll learn how geologists actually read Earth's multi-billion-year-old diary.
All right, let's get right to it. Probably the single most important idea in all of modern geology is this. The ground is not static. It's not sitting still. It's actually a dynamic, restless mosaic of gigantic plates that are always in motion.
And this is the key to understanding how that's even possible. Earth's rigid outer shell, what we call the lithosphere, isn't one solid piece. The best way to think about it is like huge rocky puzzle pieces floating on this hotter, softer, kind of gooey layer called the asthenosphere. And that is what allows entire continents to literally drift across the face of the planet over millions of years.
And that right there is the core idea behind the theory of plate tectonics. It tells us that the entire surface of our world, from the deepest ocean trench to the peak of Mount Everest, is broken up into these massive plates, and they're all moving around, interacting with each other constantly.
And you know where these plates meet? That's where the real action happens. This is the planet's creative and destructive workshop. It's the source of pretty much all of the most dramatic events: earthquakes, volcanoes, the building of huge mountain ranges. It all goes down at one of these three types of boundaries.
So this table breaks it down really nicely. You've got divergent boundaries where plates are pulling apart and new crust is being made. Then you have convergent boundaries where they're colliding, which either destroys old crust or smashes it together to build mountains. And finally, you have transform boundaries where they just slide right past each other. So basically, crust is created, destroyed, or just conserved.
Okay, so we know what the plates are doing, but what are they actually made of? Let's zoom way in now and look at the fundamental building blocks of our planet.
So you hear these words all the time, right? Rock, mineral. What's actually the difference? Well, it's a super basic question in geology, and the answer is actually simpler than you might think. It really just comes down to composition and structure.
Here's the easiest way to think about it. A mineral is like a pure, basic ingredient. It has a specific chemical recipe and a crystal structure. A rock, on the other hand, is what you get when you mix those ingredients together. So if minerals are things like flour, sugar, and chocolate chips, then a rock is the finished cookie.
Now, every single rock on Earth can be sorted into one of these three big families. And the sorting isn't based on what they're made of, but on their origin story. You know, how they came to be. Was it born from cooling lava? Was it built up from little bits and pieces of other rocks? Or was it totally transformed by crazy amounts of heat and pressure deep inside the Earth?
Okay, here's a fun one that kind of messes with your head. To a geologist, a block of ice is technically a rock. And you might be thinking, no way, but think about it. It's a solid mass made of crystalline grains of a single mineral, the mineral ice. So a glacier is actually a giant body of rock that flows and carves up the landscape. Pretty cool, huh?
All right, so we've got our building blocks. We know what the plates are made of. Now let's get back to the action. The really dramatic stuff that happens where these plates smash, pull apart, and grind against each other.
And make no mistake, the power we're talking about at these boundaries is just immense. In just the last 500 years, volcanic eruptions alone have killed over 250,000 people. The raw energy concentrated in these zones is almost unbelievable.
So, not all volcanoes are the same, and their shape pretty much tells you everything about their personality. It all comes down to the magma's viscosity, or basically how thick and sticky it is. Think of the difference between water and honey. If the lava is runny and flows easily, you get these broad, gentle shield volcanoes. But if it's thick and sticky, it tends to erupt explosively, building up those classic steep, cone-shaped stratovolcanoes from layers of ash and lava.
But volcanoes are just one part of the story. When a major earthquake happens under the ocean, that release of energy can trigger one of the most powerful and destructive forces in all of nature, a tsunami.
It's this incredible
terrifying chain reaction. First, the fault slips, and a huge chunk of the seafloor is suddenly shoved upward. This acts like a giant paddle, and it displaces a massive column of water all the way to the surface. Well, all that energy has to go somewhere, right? So it radiates outward as a series of waves that can travel across entire oceans at the speed of a jet plane.
So you have these huge tectonic forces building mountains up, but at the exact same time, there are other powerful forces working just as hard to wear them all down again. These forces sculpt the landscapes we see every day. And the two main artists in the story? Water and ice.
And they have totally different styles. You can think of rivers and streams like precision cutting tools, carving out these deep, sharp, V-shaped valleys. Glaciers, on the other hand, they're just bulldozers. They scrape and grind and gouge the earth, carving out these massive, broad, U-shaped valleys.
And you can see the work of water perfectly in something called an alluvial fan. Just picture it. You've got this fast-moving mountain stream, just full of energy, carrying along tons of gravel and sand. The second it hits a wide, flat valley, it loses all that energy and just drops everything. And that creates this beautiful, fan-shaped pile of sediment.
And this is a stunning example of the sheer power of ice. Glaciers can carve those U-shaped valleys so incredibly deep that they're actually below sea level. So then, thousands of years later, when the ice age ends and the glacier melts away, the ocean just rushes in to fill up the valley, creating one of these breathtaking fjords.
Okay, so with everything we know about how these processes work, how do geologists actually piece together the planet's entire 4.5 billion year history? Well, they learn to read the rocks like pages in a diary.
The amount of time we're talking about here is it's staggering. It's almost impossible to wrap your head around. So to put it into perspective, if you compressed Earth's entire history into a single 24-hour day, all of recorded human history, everything you've ever read about, would flash by in the last few seconds before midnight.
But sometimes the most important part of the story is what's not there. Geologists have a word for this, an unconformity. It's a gap in the layers of rock. It's like finding a chapter ripped out of the diary. It tells its own story of a time when the land was lifted up and millions of years of rock were just eroded and washed away before new layers started forming again.
And that really brings us to a pretty profound question, doesn't it? For 4.5 billion years, these massive, natural geologic forces have written the story of our planet. But now, for the first time, humanity has become a geological force in its own right. We're changing landscapes, we're changing the climate. So when future geologists look back at the rock layers being formed right now, what will our chapter say?